All right. What are we working on today? Let's see. Let's start with some discrete mathematics. Yeah, test yourself. Okay. Okay, that's done. Yeah, cool. Okay, that's done. Write in Word how to read each of the following out loud. Okay. mm, So that is x is an element in the set of positive real numbers such that x is less than 0. No, x is greater than 0, less than 1. So x is an element in this set. Um, so we're saying we want, say, in our new set, because that's set builder notation, we're building a new set. In our new set, we want element x from the set element x from the set of positive, because of the plus at the top, positive set of positive real numbers such that x is greater than 1 and less than 0. Wait, greater than 0 and less than 1. Just don't know. Okay. Text. Just double check. Is the stream going on? Cool. Let's carry on. Okay. Now we still have A, B, C. Write in words how to read each of the following. Set builder notation to words. Okay, next one is almost the same thing, same structure at least. In our new set, we want element x from the set of just real numbers such that x is greater than or equal to, is that all? I want 0, 0, and okay, or less than, yeah, greater than or equal to 0, or greater than equal to 1. Greater than, 2, 1. Okay. Mm-hmm. Nothing. Let's see. Okay. A new set of element n from the set of real numbers such that from the set of integers. That's what z means. Such that n is greater than or equal. No, such that n is, yeah. I already put it there for us. And n is a factor of 6. Finally, we want element n from the set of integers, positive integers, which is just positive integers are natural numbers. Natural numbers such that n is a factor of 6. N is a factor. What does that mean again? Um, Factor of a number, factor of a number, factor of a number. What does that mean about another number exactly? And example of factors 12. Oh, okay. Numbers that divide this number evenly. Without number. A little embarrassing, but yeah, it's math for you. Having to check those simple definitions out. Almost. Yeah. This is my AI setup. Very useful for asking questions. Claude Opus is really good for asking questions. Really, really good for asking questions. Set as default. So factor of a number 12. I think I'll just put that down. Okay. Just factor. I mean, probably learned this stuff, in elementary school, high school, but it's been a while, so yeah, just gotta put it down. Factor of a number x is any number y such that x divided by y equals to n, where with no remainder. Yeah, yeah, and with no remainder. Yeah, no remainder. Yep, makes sense. Makes sense. Makes sense. Makes sense. Makes sense. Okay. Okay, that's 4. Let's move on. Is 4 equal to 4? No, because 4 is a number and traces 4 is a set. How many elements are in the set? There are only 3 elements because duplicate elements are collapsed. Like sets can't contain duplicate elements. So that set 3, 4, 3, 5, it's equal to just 3, 4, 5. So that's going to be 3. And how many elements are in the set? 1, 1, 1. So this one is a little interesting because 1 and the second element is a subset because it's a set within a set. Actually, no, that's not true. It's a set within a set, not necessarily a subset because actually it is a subset because the set contains the element 1, which is also in the outer set because it's the first element of the outer set. So it is a subset. Yeah. So subset 1, 1, 1, 1. You think you know all this stuff, but then you go back to the fundamentals and you learn new things. Um, the simple stuff is represented in novel ways that kind of test your understanding. It's very interesting. So let's see. One, yeah. So how many elements are in the set? One, two, three. 3 elements because this last element is a single set, and a set is treated as a single element. So that's going to be. It's not like it's going to be. Yeah. So it's a set is considered as one opaque element, one unit. So that's going to be 1, 2, 3. 1, 2, 3. Yeah. And there's no like deduping here because these aren't like um primitives values entries. They're not like it's on deduping. I think deduping probably only hmm. So I don't think it'll make sense to dedupe in this case because you aren't dealing with elements of the same type. So like one is an integer, one like the first element one is an integer, the second element is a set. You there's no notion of equality between a set and an integer. And although the second and the third element are sets, they're not equal because um yeah they're just not equal. The third element would be considered a actually the second element would be a proper subset of the third element because the third element does contain all the elements of the second element. It's confusing, but the third set does contain all the elements of the second set, but with an additional like element, which is that uh, set of one again. Actually, it is. Yeah, it's confusing, but that's correct. Yeah, it's confusing, but I think that's correct. Um, hmm, 3. It's 1. So 3, yeah, 3. We'll finish this column, then maybe get to some Haskell. Yeah. Is 2 an element of the set? Yes, it is. Yes. How many elements are in the set? That's 1. Again, deduping that happens in sets. How many elements are in the set? 2 elements. Now, this actually kind of ties back to an interesting notion in set theory of like encoding the idea of order. Um, it's interesting because like this is what like so I wish I had like a board, something I can draw on. Um, but I say that's interesting because like this. Uh, actually, no, it's not the same. I was thinking of this. Yeah. So basically, the left hand side. Fuck, something wrong with my notation. Okay, yeah. No. Yeah, cool. So the left hand side and the right hand side are equivalent. Left hand side is a way of representing the notion of an ordered pair using just set elements, which is interesting because sets themselves are unordered. 1, 2, 3 is the same as 3, 2, 1. It's the same as 2, 1, 3. All of that is the same. Sets have no notion of order. But the reason why this works is because there is a specific way that we can decode this that would always give us A and B in that order. A being the first element and being the second element. The book actually talks about this. It's somewhere. Subset. Uh, no, not there. Yeah, I wrote a whole bunch. Yeah, the notation for ordered pairs is actually syntactic sugar. Like this notation, this kind of symbols are actually like an alias for this. That is, A, yep, they mean the same. How? But my notation is a bit informal. So blah blah. Seems like a way of modeling elements. Yeah. So this is a way of modeling um, A and B that is capturing the order A first, then B, using just set notation, like syntax from set theory. Modeling and encoding elements in a way that makes it possible to extract and parse out the original ordering intact. So if A does not equal to B, we can get back A then B. If A equals to B, then we just get back A or AA. So yeah, it is pretty interesting. And this works for like any, like it generalizes to tuples. Um, so we do that by like nesting. So if we want to represent ABC, we'd have to find a way to make this to put this in a form AB. So we nest AB to be like one thing and C and kind of work through that to into the like set notation form. Interesting stuff. Not particularly useful, but it's the kind of esoteric that's just interesting to know, at least in my opinion. How many elements are in a set? So we've answered that. Is yes, it is 0. No, 0 is not. Which of the following sets are equal? One, two. This is real numbers less than 3. Lots of real numbers that are less than 3. They're not equal. Let's see, -1 would be included here, but not in here. -1, 3. This one doesn't make sense. Well, I mean, D, E, we can actually program this in Haskell to check, but I would say A, D, and E. 0, 1, 2, X. X is an integer. X has to be greater than -1, so that's 0, 1, 2, less than 3. X has to be a natural number. X is greater than -1, that's 0, 1, 2, so A, D, and E. So A, D, and E. Let's actually play around with some Haskell. Check. Um, let's see. So we have A equals to uh, X. This is called list comprehension, but it's taken from or derived from, or it has a correspondence with set notation in set theory. So yeah, that's how that works. Python also has this too, um, but Python is not as good as Haskell. Let's see. What do we want? I always forget. Okay, I don't use set notation, list comprehension a lot in Haskell, so I always forget like the syntax. Gonna be, I think X has to be from that's true. We can't enumerate proper infinity. We have to have a starting point. So I don't know if this we can model this in Haskell. Hmm. Mm. Oh well. But how do we do that? Because we want to first say, okay, uh all integers. So that's negative. Well, actually, I guess we could do that and say uh, d is equal to x. You can use the bounded type class. So go min bound. Uh, min bound, max bound, uh, comma x is yeah, where x is greater than -1, x is less than 3. We have to, I think this will fail because we need to have a type specialization. Oh no, it doesn't. Yeah, it'll fail. Yeah, it's ambiguous. D I'll have to be int. Okay, still have to. Oof. Yeah, this is gonna take a while because we have to enumerate through the entire, coordinate, like the entire size of the int type, like this from the smallest int value to the largest int value. So that's gonna, and it's not exactly one to one because the set z is like infinite. All the numbers, negative, positive, all the integers in the world, the ones you know of and the ones you don't know of, all of them, every single one of them. Yeah, this will this will take a while. I am not gonna wait for it though, but I think this is correct way. I wonder how do you make this faster? I mean, where x is it greater than, yeah, greater than -1 and less than 3? Maybe I didn't write this properly, but yeah, I have to enumerate through all of them and check the condition for each of them. Actually, wait. Oh shoot. Ah, no, no. Yes. Ooh, before it ate up all my RAM. Oh no. Oh no. Oh, damn it. That was fun. Ah, okay. Thank goodness. Are we still streaming? Are we still streaming? Okay. Hello. Hi. How's it going? I should probably figure out a way to like get my stream chat overlay or something. Let's see. Stream, Twitch. stream chat overlay OBS. Stream browser source. Do I set up Twitch? Let's see. Consider using any tools. OBS. Hmm. Okay. Let's see. Stream elements. Yep. This is my first stream. So I am trying to figure stuff out. Please bear with me. Get paid for doing what you want most. Okay. Hmm. Maybe I'll look into this for the next stream. Next stream. But yeah. Okay. So back to discrete math, people. Back to class. 6. Yeah. It's okay. For each integer n, let t let Tn equals to n square. How many elements are in each of Tn2, Tn1, Tn0? Justify your answer. So each of t square and 2 square -3 1 0. Well, let's see that, shall we? So t t2 would be, actually, let's try and do this. Hmm. I don't know how this works. Don't know how I can get this to work, but um, so well. Anyways, we know Tn equals to n square, so that's always going to be like 2 elements, unless n square and n are the same, which is only true if n is like 0 or a negative. Yeah, if it's only true if like n is 0, I should think. Let's see. So t2. So let's write that down. Actually, uh, should only have should have 2 elements most, unless uh n is equals to n squared. In which case, uh, t n would have only 1 because no duplicates in the sets. It would be nice to write a proof for this, but I don't have the facilities for that. And I'm still learning how to write a proof. Justify your answer. Because how many elements are in? Let's do T2. That's going to be 2 and 2 squares 4. It's going to be 2 elements. T -3. Oh, we should get started on some Haskell soon. T -3 is gonna equal that's gonna be -3 and 9. So that is also 2 distinct elements. T1 gonna be -1 and it's gonna be 1. 1 square is 1, so that equals to 1. And T0 is probably the same. This will be the last before we get into some Haskell. 0 square is 0. Yep, cool. Okay, that's enough of that. Time to get to the fun stuff. The fun stuff. The fun stuff. Ah, the fun stuff. Back at it. I was parched. So I had to go drink some water. Now I am no longer parched, so we will play that shit. Okay, back to this beast. Where were we before? Wait, it's almost there. I'm almost. Oh, okay. I think I remember. We were trying to. Right. So we just implemented RDB snapshots, which is like being able to basically serialize your entire Redis store to disk in case of a crash or just for like for backups for redundancy. So we've implemented that. It was a whole thing. Unfortunately, I did not stream that, but it was a whole thing, and I probably should have streamed it, but I didn't. Um, but it was a whole thing. Um, yeah, so that's been implemented. Now we want to write tests for it, all in sweet Haskell. Okay, let's get to it. Nice. I left myself notes. Good on me. I should give myself a pat on the back. So I was considering making this a prop test, but it looks like this test below kind of covers all the bases, which is like, okay, we expect it to be, we should probably move this to the bottom, but this is what our RDB file will be. That is the file that we're gonna, that's the snapshot file. So the initial store would be this key one. Uh, oh, and yeah, I think it's coming back to me. It's coming back to me just bits at a time, bits at a time. So the initial issue was that I was in my store model. That is the way I was modeling. Huh? Really? Anyways, the way I was modeling things before, yeah, store data. Actually, no. Server state. So with the way I was modeling things before, the snapshot, the RDB snapshot, it would be impossible for like the once we kind of reserialize or reload from the snapshot, it'll be impossible to kind of so if we go back to the test, what we're doing here is we have the initial state. Um yeah, then we're just running some set commands to add stuff to the initial like to the Redis store to add to extend that initial state with additional stuff. Um, then the save command is us, running the snapshot called like creating the snapshot. Save command which we run here. And the initial server state is mutable, so these changes will persist. Uh, STM for the win. So the result save command. Yeah. So we perform the snapshots. The result is something like okay, whatever the Redis RESP protocol. I always forget what the name is. Like which tab? One of these is my Redis tab. Which one? Yeah, this is probably it. My Redis window, all the Redis stuff. So RESP is the protocol for communications between a Redis server and a Redis client. Think of it like, how in JSON on the web, you have like JSON. The server will send JSON over to the client. For Redis, it's a TCP layer. That's a layer 3, layer 4, layer 1. Layer 1 is like bare metal stuff. Layer 2 is like MAC addresses. Layer 3 is IP. Oh, it's a layer 4 because layer 3 is IP addresses, IP stuff. Layer 4 is a TCP and ODP. Yeah. I have OSI model. Double check. Yeah. Okay. Yeah. IP, TCP, UDP, not ODP. Yeah. UDP. Um, so it's a TCP protocol. So it doesn't like have all the bells and whistles to work with like JSON like a regular web API would have that would allow it to like send JSON over, read JSON. At least that's kind of my understanding. So it uses the it has its own like serialization format, RESP communication format or data marshalling format called RESP. What does RESP even like stand for completely again? I forget. RESP Redis. Yeah, so Redis serialization proxy. So it's a serialization format for communications between a Redis client and a Redis server. So we have a partial implementation. It's not a full implementation because we are actually working through Code Crafters. This is not a sponsor. This is just like Code Crafters is awesome, and I am currently working through the build your own Redis track. It's not like holistic, but it kind of goes deep enough that you are learning a lot about Redis as a piece of software and yeah, learning about like it's how it works. So you can see here TCP service because Redis server is a TCP server. Um, and my guess is that the reason why we don't like use JSON is because like we're missing a lot of the because with each additional OSI kind of layer, we build on top of the previous layers, adding stuff to make like network communications more robust, more reliable, more yeah, more robust. So hmm, that's actually a really good question. Why doesn't Redis use JSON? That's actually why doesn't I guess part of that would probably also be bandwidth because JSON is probably it's a pretty like compared to you know RD the RESP and like binary or gRPC those kinds of serialization formats. JSON is a lot more, it's a lot heavier, takes a lot more bandwidth. So why does TCP not why does Redis not use JSON? Why does Redis not communicate using JSON? Let's see. And this, ladies and gentlemen, is why I like why LLMs are really useful because you might have to like synthesize answers from different sources online, but like with an LLM, you can always just ask it and then verify your answer. Always verify your LLM output. Let's actually see what Opus tells us. Yes, instead of JSON several key reasons, simpler to parse. Yeah, less bandwidth, less overhead. Um, it's 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 faster to kind of send RESP than send JSON because JSON is more chunky. It's chunky. Yeah, so faster, and it's a simpler format, so it's faster to kind of serialize and deserialize. Even though like a lot of developers have like their libraries out there that make it a single function call to do the whole serialization and deserialization, but like it's pretty straightforward to write out a parser for the RSP format because again it's just text and it's smaller too. So binary safety, okay, that's a big one because Redis does allow you to kind of store blobs. So you'd want that kind of binary safety. And binary safety is just a case of like, if you give me a sequence of bytes or like binary, I should give you back the same. Like there shouldn't be any transformations happening on that binary data. Which it's kind of like idempotency in a way, which or no, not idempotency, but like referential. Actually, no, let's not bring in those terminologies. It's kind of like what you give me is what you get. So like you give me binary, get back the exact same binary. You don't there are no transformations happening. It's just like take it in, give it out. That's what binary safe means. So yeah, so this makes sense and this tracks kind of my understanding. You don't want to use JSON at that level because like uh you probably don't well I'm actually not even sure about all the bells and whistles bit about like higher OSI layers. That's probably rubbish on my part. But the the notions of like RESP being a simpler format, having less bandwidth, um, and simpler to parse, serialize, and deserialize from makes a lot of sense. So that is why we don't use JSON for its protocol. Yeah, should probably write this down somewhere. I'll put a sticky notes. Symmetric bits. Symmetric bits. Uh, this is a sticky notes. Let's close this one. Other color. Um, yeah. Why doesn't why don't Redis servers just communicate using JSON. Put down. Okay. Into yeah. So I guess I think just generally speaking, RESP is just a lot more efficient for the use case of a Redis server. And it's probably also it reduces latency too. Yeah, it reduces latency, making it yeah more efficient. So it's a kind of self-fulfilling prophecy there. So that's my sticky note. So let's get back to the do. So we want to this return us like an RESP response. RESP responses are kind of predefined by Redis has this whole list of commands and their responses. This is Redis configuration. No, what I want is duplicate this tab. What I want, yes, I am a tab hoarder. Uh, commands, commands, docs. Yeah. So like if we go to save, well, it does not work. That's pretty shitty. So yeah, we can see its response to the different versions of the RESP formats. This is RESP is a most recent one, so it's just returns OK as a simple string, uh, which is what we have here. We expect it to give us back OK. We should probably call this respected uh, save command response. Good names save lives. Remember, kids, if you don't use good names, good variable names, you're only hurting your future self. So, yeah. Result test server. So, yeah, so this creates a snapshot in the file that we defined up here. I'll create the snapshot. Then we check if the snapshot exists. Uh, then we try to reload the snapshot back into like our data structure. Um, Yeah, so we take the file and kind of reparse that into data structure, our internal representation of what that snapshot is, which is the RDB file. Um, this is just for debugging purposes. Then we load it. That means we parse through the RDB file structure here and try to recreate a store, a Redis store. Now the issue here is that due to like how we actually store stuff in our Redis store implementation. So if you go to server state, you can see a Redis store. Our store is just a hash map of store key, which is a new type, and yeah, that's here. Um, I think keys should also be binary safe. I think, yeah, I think keys should also be binary safe, which is why we had this as byte string. Let me double check that actually. Are Redis keys binary safe? Yeah, so binary safe. Byte string makes sense. And a byte string is just what it says on the tin, a sequence of bytes. Sequence of bytes. What's my Does that actually work? Sequence of bytes. So it's just a sequence of bytes. Um so should I just probably put it there? Redis keys are binary safe strings. which shows an easy way to like link to this text specifically. Like text links, especially in Firefox, are ugly as shit. Okay, no, they're not. Uh, anyways, so store key, store value, store key, store value. Yes, so Redis does not store insert time slash time of creation. So the issue I was running into was that the when we serialize from our store, we kind of lose the insert time. That's actually there are two issues. The first issue was the insert time. When we serialize, we strip away the insert times because that's not a part of the RDB specification. The RDB specification does not support or include any notion of like the insert time because Redis itself does not store insert times. So by us storing insert times, when we go to serialize our store into the RDB format, um, we strip away the insert times, and when we go to reload that, that is recreate a Redis store from that snapshot, we have to kind of use the time of at we have to use the time at the point when we're loading it, when we're parsing the RDB snapshot file into a store. That time has to be the new insert time, which is technically right, but also kind of wrong. But you can see like how the original information got lost in the process. So that's preventing this test from passing because it'll never these two store from snapshots and store from server states. This is not the yeah. Well, stores from um is there a better name for this? Store from non-snapshot server states. Non-snapshots. So store from non-snapshot server states. Yeah, those two will never be equal because insert times are going to be always going to be different. Another issue was that we're using the UTC time type, which is like a representation of like time. I don't particularly have a good uh have a huge amount of clarity into the details, but it we would run into issues of like precision because when we are serializing to the RDB format, we're trying to like yeah serialize to the RDB format. We'd have to kind of lose precision so that we can like have a whole number to store because that's how Redis wants us to like store um those timestamps. Uh uh, as a millisecond, like Unix timestamps, milliseconds. Well, apparently Unix timestamps are actually in seconds. But JavaScript, the bastard, is stored has its own Unix timestamp in milliseconds. But many languages, I think the standard is to have them in seconds. Um, but Redis actually uses milliseconds underneath the hood or internally. Even though it supports seconds, it actually just converts everything to milliseconds because, more precision never hurts. Greater precision never hurts, and allows greater precision of like when to evict entries, keys, all of that stuff. So um, yeah, so UTC time was a specific was a it was super precise, but it used like floating point numbers or fixed point numbers to like represent time to represent time, and the issue there was that we'd have to convert that to a whole number, and because we did that we'd lose precision because in the original store we'd have it as a you know fixed points floating point value, the time stamp. um then in order to get it to the RDB snapshot we'd have to like model like we'd have to integerize, that's not a word. We'd have to floor seal it, like floor it. We'd have to like round it down to, do the usual conversions, then convert it to a whole number, you know, save that to the disk. But when we're reading it back out, we've lost kind of all the precision that we'd usually we'd lose all the precision that we had going in. We lose all the precision that came after the decimal point, the radix point. In the initial kind of representation, we lose all of that precision. So that's another reason why I hope that made sense. It felt like there were lots of like gaps, in between. But to reiterate, initial store would have, think a number like 1 billion or 200,000 dot 5432111 whatever. But when we're going to the Redis, when we're converting, serializing that into like the RDB file, we'd have to let go of the everything after the decimal place, do some conversions to convert it to milliseconds, or whatever. Uh, convert it to a whole number. We'd lose all the stuff after the decimal point. Um, and when we try to read back that snapshot into a store, it's totally different kind of time representation than what we had initially. So those were the two issues. The issues with the insert time never being the same between like the initial store and the store after the snapshot. The initial store and the store read from the snapshot, and the um the the loss of precision for TTLs, the timestamps. So that's a lot of words. Let's actually get to some code writing. So we have, it's a word because, I've never known time to be a negative number. So maybe in a sci-fi, I wonder what does that actually mean for time to be a negative number? I wonder what that means. Does it mean we're going back in time? Hmm. Food for thought. Food for thought. Food for thought. Food for thought. So we have this Unix timestamp now. This is what we want to milliseconds. We have functions that would take us from to, yeah, POSIX time. POSIX time is like, it's think of it as like the library's version of a Unix timestamp, but it's not um a whole number. Still, it's still like it's a fixed point number. I think it's a pico underneath, which is a fixed point, like super high precision fixed point numeric value. Haskell is fun. So basically now we want to, so we've been using UTC time from the start, and we now want to replace it with like Unix timestamp. So let's do that. The beauty of Haskell is that the compiler will tell you all the places where you need to fix shit. So let's do a stack build. We don't want to check the tests. We just want to check the actual source code for now. Okay, so this is place one. Uh, Store value. Yes. Okay. Right now, we only support storing string values. Yes, I know there are a lot. Yeah, we only support string values at the moment. Okay, so TTL, maybe pure. Okay, this is forget. So if there's nothing, we assume then there's no TTL, meaning it never expires, meaning we can always just retrieve. But if there is a TTL, we have to check if the TTL has expired. Wait, what the fuck? Okay, oh yeah, there's no timestamp. It's just TTL. TTL, BBL. TTL, we want to use this function. Mm, 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 Yeah, no ordinance. Mhm. Okay. Okay, so that's fixed. On to the next one. This is fine. That's fine. That's just another warning. Do we want tag annotation? I don't know. We'll come back to that later. Okay, so we want, this is going to be tricky. So we want to set up TTL timestamp. Okay, where do we use this function? Current time. X. Yeah, we want get current time. Maybe we should make a function called get current time. Mm, mm, It was just fmap. Mhm. So that will give us, it should take a TTL timestamp is what? Mm, Maybe, just maybe. Oh, we probably want Unix. Yeah, probably don't want no TTL. We don't want no TTL here, son. Don't give a fuck about that. No, no, boy, no, boy, no. Do we need these conversions anymore? Let's see. Let's look for all the places. Oh, okay. TTL options. See, that makes sense. Okay, current TTL for item. That makes sense too. So case seconds, okay? Mm, TTL times now. UTC time. Integer. Actually, just instead. I see what we're doing. We're adding to the current time. So it's oh, we're adding to the from the current time and whatever this is. So we have to convert this to second. Okay. Let's see. So we take current time. Current time the best name. Okay, current time, yeah. T. Probably call this offset in seconds, something like that. And we untag it. Is integer the best type here? Are integers the best type here? Probably. Probably not. Technically, this should be words because they are non-negative. Then we want to go from seconds to milliseconds. Taking the current time and adding that amount of seconds. Offset in seconds. There a better name for that? Um, well, double. Gives us back a double, which is mm, that seems pretty roundabout. Honestly, why not just treat it as why not just treat it as an integer? Milliseconds to seconds is what? So if we have like 1,000 divided by 1,000, like 1,000 seconds. So wait, we want to go from milliseconds to seconds. Make this small. Seconds to milliseconds is multiplied by 1,000. Yeah. So we shouldn't need the conversion to millis from. We shouldn't need to do any conversion at the milliseconds level because this is already in milliseconds. So at least it's already in milliseconds. So we can just go back and say it should also be a word. using tag types because tag types are cool. No need to do any division or conversion. We can just treat them as milliseconds. No conversion. Tag types to disambiguate without having to create new types. Probably need to exchange. Uh, probably need to um, just make all of them word, honestly. Positive integers cannot accept negative integers and accept as large as we want. So here, offset in seconds will be a word, but we treat that word as being a value in seconds. So when we untag it, we can just go from seconds to milliseconds and add that to the current time. Uh, yeah, create a new timestamp. PX, we treat offset in there better names. Let's see. There better meaning for this given context. Use Opus Sesame. Detail offset. Oh, what a waste of tokens. I could have come up with that. Shit. But it's fine. TTL offsets in seconds. TTL offsets in milliseconds. Okay, cool. TTL offset in milliseconds. Don't need any conversion. Actually, we don't even need our DTC time. We're just gonna do good old summation. Yeah. Since we're not dealing with UTC times anymore, we're dealing with good old summations. Redundant brackets. Bracket, nice. Xsats is what? I always forget. That is Unix time. So timestamp in seconds. So we want to go from that. That's a seconds value. So you want to do seconds to seconds. Yeah. Then that's just it's just milliseconds. So just these are just these one we add to the current time. This one just like give me the timestamps exactly. So TTL time stamp in seconds. 2000 seconds. We have tests, so we don't got to worry about regressions. At least I hope. Oh, now we get syntax highlighting. Make store value. Ah, we don't need the current time anymore. No more insert time. Set. Mm, ah, current timestamp, milliseconds. Okay, we don't need. Cool. I think this is done. Ah, so we say numbered. There's stuff there for a little bit. Well,